In this module, we'll continue with drawing Lewis structures, Lewis structures part 2. So after you've gotten that far, like in the first video, the next step, and always do this, make sure you always do this from now on whenever you draw a Lewis structure, calculate what's called the formal charge. This is the formula right here. All you do is you take the number of valence electrons that the neutral atom has, subtract out the number of lines touching that atom, and subtract out the number of dots on that atom. So for example, all of these oxygens look just the same in this structure. This is sulfate. We're continuing on with sulfate, by the way. So there are 6 valence electrons in a neutral oxygen atom, minus 1 line right here, minus 6 dots, 2, 4, 6, adds up to be -1. The formal charge on each of these oxygens in this structure is -1. For sulfur, sulfur has 6, the neutral sulfur atom has 6 valence electrons. I don't mean in this structure here, I mean when it's just a single neutral atom of sulfur. 6 valence electrons minus 1, 2, 3, 4 lines, and 0 dots is +2. Okay. So why do we do this? Well, it ends up that we can use formal charges to try to get a better picture of what the real molecule looks like. So here's how you do it. First thing you do is you try to get the smallest size formal charges. What's going on here is there will be often times when you'll have a choice. You've done everything we did in that first video and you have more than one good structure, at least up to that point. How do you choose between them? Which is the better structure? Which most closely represents reality? Well, formal charges help you to do that. The first rule is that the one with the smallest size, that is the magnitude, formal charges, is probably closer to the reality. What do I mean by smaller size? Well, I mean that, -1 is smaller than -2. +1 is smaller than +2. 0 is the best. You can't always get 0. Matter of fact, whenever you add up the formal charges in a molecule, they will have to add up to be equal to the overall charge in that compound. Now remember, it's the sulfate polyatomic ion that we started with had a -2 charge, right? So when we add up our formal charges, they have to equal -2. If they don't, we did something wrong. So if you add these guys up, you'll get -2. That's how it should be. But what that means is that, and we know in this molecule, we will never be able to get all zeros for formal charges. Also, given a choice, once you've done everything else, if you have a choice between a formal charge being a negative formal charge being on one atom or the other, it's better to have it on the more electronegative atom. Likewise, if you have a positive formal charge, if you have a choice, it's better to have that positive formal charge on the less electronegative element. So now here are some exceptions to the octet rule, and there are quite a few exceptions actually. So the first one is that when you're adding up the valence electrons in the very first step, if you get an odd number, you'll know right there that there's no way that all of the atoms will be able to have their octet rule satisfied. There's going to be one atom with less than an octet. In nitrogen monoxide, for example, if you count them up, oxygen has 6 valence electrons, nitrogen has 5. That gives you 11. So right there, you know that there's one of the atoms is not going to have a complete octet. So you go through and you draw the Lewis structure as normal. Now, I ended up with this structure right here. You should go through the steps yourself and see what you get. But there's also another structure where you would have oxygen not having a complete octet. It might be something like this. See here, each of these guys, nitrogen up here sees 1, 2, 3, 4, 5, 6, 7 valence electrons. Oxygen sees 1, 2, 3, 4, 5, 6, 7, 8, and the opposite's true down here. Now, if we calculate our formal charges, nitrogen has 5 valence electrons, minus 2 lines, minus 3 dots is 0. Oxygen, I'm doing this structure right here, has 6 valence electrons, minus 2 lines, and 4 dots is equal to 0. All right, now let's do it for this structure. This is why I didn't draw this structure here. So I'm going to erase this guy over here. So now we're doing the structure right here. Formal charge on nitrogen, 5 valence electrons minus 2 lines minus 4 dots is -1. And oxygen, 6 valence electrons minus 2 lines minus 3 dots is +1. They still add up to 0 because there's no charge, so that's good. But we have formal charges that are bigger in this structure than they are in this structure. And that tells us that this top one right here, this is the one that most closely represents reality. So the next exception are some specific elements. Boron and aluminum can be satisfied with 6 valence electrons. They don't need 8 valence electrons. So for example, in aluminum chloride, when you draw the Lewis structure, you use up all the electrons. This is what you get. Now, you could certainly draw a double bond. But when you do, a couple things happen. The formal charge on this chlorine now is 7 valence electrons minus 2 lines minus 4 dots is +1. And aluminum is 3 valence electrons minus 4 lines is equal to -1. 1, 2, 3, 4. That's not as good as what we originally had. Which was this? If you calculate the formal charge for all the elements here, they're all 0. Boron is like that too. Now beryllium, it's satisfied with 4 valence electrons. It's, for example, in beryllium fluoride. This is the structure right here. By the way, we know experimentally that the real structure for aluminum chloride looks like this and not the double bond. Because we can actually measure these things. We can tell. We have spectroscopic techniques that let us peer into this molecule, and we're able to tell if a bond is a single bond or a double bond or a triple bond or what have you. And we know experimentally that all of these bonds are identical to each other and they're all single bonds. The next exception is a huge one, and it says that any element in the periodic table that's in the 3rd row or lower can have more than 8 valence electrons in a Lewis structure. Well, the 3rd row, that's the one that starts with sodium. So there's a lot of elements there that can violate this octet rule, but that's the way it is. Now let's go back and look at our sulfate polyatomic ion. This is a point where we had gotten to. Now that we know that we can violate the octet rule and knowing about that these formal charges aren't that good, right? This +2 formal charge is really ugly. That's a big formal charge. We don't like that. Everything within formal charge. So if we were to make a double bond, say here and here, and see what I've done, is when you make a double bond, is what you do is you take 2 dots from that are a lone pair, and you draw them as a line. Now that's a double bond between this oxygen and this sulfur. And I did the same thing over here. And you see what that does for us is that gets us a 0 formal charge here. You calculate it, see if you get that. 0, 0, -1. Let's write those guys in. -1, but sulfur now has 0 formal charge. And that's the best we're going to do. A couple of reasons we know that. One, because there are 2 negative charges, we know that we have to have 2 negative formal charges in the structure. Also, we know that oxygen is more electronegative than sulfur, so if we do have to have a negative formal charge, we'd prefer it to be on the oxygen rather than the sulfur. And we don't have a -2 anywhere, it's just spread out as best we can. So there's the structure for a sulfate polyatomic ion. Now we're going to talk about resonance forms. So don't let those exceptions to the octet rule catch you unawares. Make sure you know about them because you run into them all the time. All right, so resonance forms. Now, back a moment ago when we were drawing the Lewis structure for sulfate, I put the double bonds here and here, but I'm sure you noticed I could have put them as well between any two oxygen atoms and you'd get the same quality formal charges. Whenever you run into that point, when you have a choice as to where to put electrons in a Lewis structure that gives you equally good Lewis formal charges, that tells you right there that you're going to have resonance forms. So for example, I could have, instead of putting one of the double bonds here, I could have put it down here. These are resonance forms of each other. And it ends up that there are 5 other resonance forms, which I'll show you them all in just a second. But what does that mean? Well, first of all, and this is really important, there is only one structure for sulfate, for example. And it's not that the electrons are moving back and forth really fast. They're not. I mean, we draw this double-headed arrow to show resonance forms, but it doesn't mean they're flipping back and forth. What the real structure is an average of all of the resonance forms, which I'll show you in a minute. Now, remember, before we knew about formal charges, let's go way back. We were right here. Now, this structure for sulfate, it does contribute to the actual structure for the sulfate polyatomic ion, but not as strongly as the one with the better formal charges. So catch that, right? The structures with the better formal charges contribute more to the real structure for a molecule than structures with less good formal charges, but it doesn't mean they don't contribute at all. There is some contribution to the real structure for sulfate. Looks, okay, here we go, looks something like, well, a lot like an average of these. These are all of the 6 resonance forms with the best Lewis structure for sulfate. There is also a structure that looks like all single bonds between the sulfur and the oxygens. That doesn't contribute as much. So here's how I think about this. I start out with one. Let's just say this one right here. What I do is I keep one of these double bonds anchored and I rotate the other double bond around the other atoms. So here, here, and here. Then I take the first double bond and I start out on a different atom here and I rotate the second double bond between this one and this one. I don't go back to here because we already took care of that structure up here. And then I rotate it one more time. I start with the double bond here and I put the second one here, and anything else we've already covered. So that's a total of 6 resonance forms for the best Lewis structure of the polyatomic ion sulfate.